I'll post the solution, but it should have been straightforward. You have a system that you can find a transfer function, right? What is a transfer function? The ratio of output to the input. So op amp Vp equal to Vn, the Ip equal to In equal to 0. So you solve for Vo over Vi. You have had this before, it's just like a bunch of, like you just write and get the transfer function. So this is the information from the system. What other information you had in the question? You had the output, how it's going to look like, right? So you had the output in time domain, and you knew it was the response to a step input, right? So now if you write that output in time domain, in S domain, and you already know what the input is in S domain, you can find the relation between output to input. Now you have two things that say the same thing. Put them equal to each other. You will get relationship between your components from just putting these equal to each other. Now, where is the design issue? Where did the design issue come from? So this is part of it. Now you will get, for example, I think, let's say, I think it was R1 times C is going to be 1% or 0.01, right? So it tells you that you can pick this as long as this relationship holds, you're good. You can choose anything, right? You have another relationship for R2 and R3. All right, now you can pick anything. Then how do you check if your solution is good or not? You can look at the response of the system, right? Find the steady state error. Do you get 0? Because you want to get 0 steady state error, right? If you don't get 0, it means that you are farther from that. So you have to manipulate your values a little bit to get to that 0 steady state. All right. So this is where design comes from. Because I think a lot of people thought this should have been a very difficult example, like try to like incorporate the error from the question I got from the student. But no, usually the solution is simple. But how to arrive to that solution is the difficult part. Again, you hired me for saying that with critical thinking. What information I have currently, what I have in information and skills I had previously, and how can I combine these two to arrive at something that I want, right? So for this, if you found the relationship between the components, it's good enough. But if you went one step further and you said, okay, let's choose these values for my resistor and capacitors, and then here's the steady state error. I expect to get 0 for a good design, right? If you didn't get 0, so it means that you just have to change them. So these are, I'll count these as the, I'll count it as extra miles, but all you should be able to find a relationship between the components. That's where design, so that's where you start designing from there, right? So hopefully everyone kind of was in the same direction. Not from the first look I had on the assignment, but again, it's a good opportunity for all of you to learn. I chose on purpose because most of our examples were mechanical. You're electrical engineers, so my assumption is you're better in electrical analysis, so that's why I chose that. I'll post a solution on Carmen tomorrow at time, which will be tomorrow. And so far you have so much knowledge. You're not going to use all of them in all problems. You need to be able to choose what knowledge or like I'm using, what information from past I will be used in this certain example. All right. Because when you're doing homeworks, you know that, oh, I'm going to be asked question on this certain topic, right? But in real world, nobody tells you what's the topic that you need to go and grab from the memory. So you should be able to understand what is it that I'm trying to find. Does that make sense? So at least your one takeaway point from this class participation should have been, because this wasn't directly related to system type or errors, right? It should be that in real world, nobody tells me what I'm being questioned on. Can I understand what the problem is? All right, cool. Last class, we stopped on the bigger problem for Hubble telescope, right? There was a couple of system requirement, and we wanted to come up with gain values for our system. Again, that's a design decision. You will always find a range or a combination that you can choose. There is no one solution. Forget about one solution in designing a controller. Before that, I thought I'll give you a quick review of the non-unity feedback system, that it's important, and you're going to have it in your homework, so maybe give you more insight into that. If you remember, all the system type, everything we discussed was unity feedback system, right? For non-unity feedback, we have to go to the main equation of how do we calculate error? So R minus Y, your input minus your output. And then if we can find the relationship between input and output from the transfer function of our system, we can replace our output with transfer function times input, and then we can find a relationship for our error. If you remember from last time, if we have a non-unity feedback system, our error becomes RS times 1 minus TS. So you will find the transfer function, and then you can always use this equation for non-unity feedback. Then after that, since you have your E, the rest of it is the same. So the steady state error is limit of S times E. And then since you have E is S RS 1 minus TS, you have your input. You can evaluate the error for different kind of inputs, right? Step, ramp, parabolic, but your transfer function is the same. You're not changing that. You could have information about type of your system, but that's all you can, you would know. For non-unity feedback, there is another way, like an alternative way of converting them to a unity feedback system. Then you can use all those great tables that you have. So one of the example I showed, like in the lecture, I used this but never talked about it. So if you have a non-unity feedback, look at this up here, GS, HS in the feedback loop. I can add, so this is just for block diagram reduction. So this is ridiculous. You can never have a negative feedback line and positive feedback line. This is to manipulate the block diagram reduction. If I add a -1 signal and a +1 signal, I didn't add anything new to my system, right? So adding plus and -1. But doing that, I can get a feedback. These two now are in parallel, right? So I can reduce it to this block. Then you remember, you can reduce the inside block. I reduce that to this function. Now I have a negative feedback loop. The system looks different, right? Remember, this is just to trick the block diagram to be able to use that table. So this is not your actual system. This is a fake system we created, so we can just use that table for position error, velocity error, and acceleration error. If this is something you're interested, you can do that. Otherwise, you can go from the main equation, find E, get that limit, and it would work nicely. All right. If you're following the book, your book is doing this, is using this method. It doesn't explain. It says that after some block diagram reduction and adding a negative feedback loop, ta-da, that's a new system. Okay, this is what is happening. If you don't like it, don't use it. Extra tool in your toolbox if it comes handy. Make sense? All right. So back to the example that we left off on Friday. I think everybody was really tired also, and we ran out of time. So we have a model of our system. It could be any system. You'll see that it really doesn't matter. After you put down the block diagram, it doesn't matter what it is. You can forget about what system it was and deal with it as a block diagram. We have, we desire to select the magnitude of our gain, K1 and K2, which I said that here this has to be K, because we only have K1 and K. We want the percent overshoot of output to a step input to be less than 10%. We want the steady error to a ramp input to be minimized. Again, it's not zero. Zero is what we want, is the minimum, but we want to minimize it. We want the effect of the step disturbance to be minimized. So we are going to check the steady state error for RS, which is a ramp, A over S squared. And our disturbance, we want to know what's the effect of a disturbance that is A over S. All right. So this is a real design problem. This is a real, I'm not going to say this, well, it is design because you're trying to pick K and K1. Sometimes you can't just solve them step by step. Okay, let's solve the first one, then let's solve the second one, then solve the third one. Sometimes you have to solve them all together, meaning that you have to consider all of them because you're designing one system. It has to apply to all three of these conditions that is being asked. Sometimes your conditions are such a way that they are independent and you can say, okay, I'm going to solve for percent overshoot, then I'm going to solve for zeta damping ratio, then I'm going to solve for time like T of S or whatever, right? Sometimes they're independent, but usually for designing controller, like picking gain, you need to consider both of them because both K's, for example, will show up. You find a relationship. You don't find exact number like CP18. There was a relationship in there. So be ready to find relationship and be ready to solve all of them together. But you have to have a process. Think about what your process is. Now, here, let's just start with percent overshoot and let's see where we end up. Now, if you're following your the file that I shared on Carmen, after this should be a plot, right? I tried to download it. It did not download on my iPad. So that, yes, that plot is nothing other than the equation for percent overshoot, e to the power of negative zeta pi over square root of 1 minus zeta squared. One of them. The other one is like T omega something. It's from your book. So look at the graph that goes down. So here our percent overshoot is going to be less than 10%. So if you look at your graph, your zeta is going to be somewhere around 0.6, right? This is as if you solved this equation. So percent overshoot is either negative pi zeta squared to 1 minus zeta squared. You also have this. Here is your, I think, is this percent overshoot and this is zeta or the other way around? Can you look at your graphs? Am I right? Okay. So I know I need to have 10%. So if I pick that line here, I think is like around like a little more than 0.6, but I'm going to, because either you have to solve this equation and say 10% is 0, 0. This is 10%, right? Yeah. Is E negative pi zeta. Yeah, you have to solve that. Either you have to solve this equation, which only has, so you have to have your calculators and you can solve for exact value. Or since this is a design problem, you don't exactly know, you can pick something that's very close. You can use that graph, say 10% looks like it's going to be 0.6. So zeta, I'm gonna say, is around 0.6. Does that make sense? I'm just reading, instead of solving this equation, I'm just reading from the plot. How did I plot it? I plot that equation for all zetas and all percent overshoots. Following? Someone say that you're following? Okay, good. I know, like I keep asking because I need feedback. Huh, funny, I need feedback into class. If you don't give me feedback, I don't know where to go after. So now I kind of know the damping of my system based on the first requirement. Then we want to have the steady state error to a ramp input, which is minimized. Now, what is your approach to do this? I took care of the first word. Find the transfer function of the system first, very quickly, right? Because whenever, as soon as I say a steady state error, what does it mean? I need to find E, which is R minus Y. Where do I get Y? From the transfer function, right? Now, if you remember from Friday, you can say that, so you have a multi-loop, right? You have an internal loop, which is part of your process. I can reduce this. What happened? I can combine them. This is just a feedback loop, right? So I will have a very neat looking, I'm gonna add a page here because this one doesn't have a page. You should have an extra page to write on. I don't. So I can have a neat looking GS, which is my plant, and is going to be 1 over S plus K1. Then I have my TD, which is my disturbance, being added to the system. Then feedback, I have K, which is my controller, amplifier here, amplifies things, negative, positive RS. So for the first part, I want to know what is a steady state error for RS to be A over S squared, right? We need to find that. Now, first find the transfer function, second, then write that equation, and you should be fine. Now, for transfer function, I'm gonna write it and you can just copy or do your own thing. So I'm following the solution in your book because then when you're following the book, if you are, you won't be confused, but at the end, there will be the same transfer functions. Yes. So T of S is here is K GS over 1 plus K GS. So if you solved it, this will appear on TDS. Now here, this is a new, so not a new term, but if you're following your book, you'll see that your book is considering the loop gain in your transfer function. So why loop gain is important? What is the loop gain here? Do you remember from graph, the what was it? Graph diagram? What's the loop gain? The two transfer function, right? You have one loop here. K times GS is your loop gain, right? It is, because you only have one loop. Loop gain was a transfer function. If you convert this to the graph diagram, the value of transfer function is the value of that line signal, right? So you had lines and nodes. The nodes are your signals. The lines are the value of your transfer function. The loop gain was you multiply all of them together. So your loop gain here is K times G of S. So this is just a change of variable. We don't need that. This is just extra information for you because at the end, since K will show up in your control design, you will end up saying, hey, if I increase the gain of my loop, such and such will happen. Just adding extra vocabulary to your control design, or extra like adding a better understanding, because the process G is in your gain loop gain, right? So let's say if we had to at the end say K has to be very large, it means that your loop gain has to be very large. So you might hear, instead of saying K has to be large, we need to choose a higher loop gain. That's just as if you wrote them separately. So this is a trivia information, extra information. Doesn't do anything because you could just use KGS and it's the same thing, all right? If you're following this on your book, or we can also write as, this just makes it shorter. E is R minus Y. So you have your R, right? And you have your Y. If you expand this, is 1 plus LS RS minus GS 1 plus LS TDS. From here, you will see that the denominator is the loop gain, 1 plus loop gain, and numerator is basically like weighting, like how much things you have. R goes to your system, then there is disturbance that deducts from that, kind of that thing, all right? Again, this is just fancy way of writing it. It doesn't add any information, deduct any information. If you don't use L of S, if you used here KGS, you'd be fine. It's the same thing, just different interpretation. All right. So let's say we have our transfer function, we have our error, we wrote all of that. Since we have disturbance and input, both of them will impact our error. Now, when we are evaluating a steady state error to a ramp input, we want to know how we minimize that. What should we do? We have two things. We have the input and the disturbance, but we only want to know the effect of our input. What should we do? You put your disturbance equal to 0, right? Because I only want to know what happens if my input is ramp. I'm not interested in my disturbance right now. So the error has both terms in it, but to evaluate, I'm going to say TD is going to 0, and then R is going to be A over S squared, because I want to know what's the error, because I want to minimize it just because of the input, nothing else. So if you haven't, for example, in your homework, one part of it, I didn't say anything about disturbance. You have to decide. And this is the procedure always. All right. So let's say that if I do that, this is basically 0. So we know our YS, this is also 0. Is TS times RS, TS is KGS 1 plus KGS times RS, right? You can either go from here and I'm putting the second round. Don't look at this right now. I want it to be, let's say it was B over S squared, just for giggles, because I'm going to use A somewhere else. So T of S, I shouldn't have taken that off, is GS over 1 plus KGS, and error is going to be RS over 1 plus KGS. So if you do that, your ESS becomes, you have to get the limit and whatnot, K over K1. All right, so here you'll see that this has to be minimized or 0, right? What is B? B is the magnitude of input. If it could be 1, right? That doesn't matter. You would know. B is given. You have it. You can say 1 from the beginning. Whatever. The thing you don't have is both of these, K and K1. We don't have them, but in order to minimize the steady state error, what should happen? Let's write this. For ESS to be minimized, what do you say about K or K1? Which one you can say something about? Jesse. We know that K has to be maximized, right? Because K1, we can't say anything for certain, but we know that K1 has to be large for this to go to minimum or be 0. Number over infinity equal to 0, right? So we know one condition. We are designing a controller. We won't have a solid number. We will have relationship, and we have to have a design decision. So K has to be a large value. Then what else do we know? We also know that for, what else do we know? Status error to ramp input is minimized. The effect of step disturbance is minimized. What should we do for that? When it says effect of a step disturbance is minimized, what is disturbance here? A over S, 1 over S, right, is a step input, is a step, correct? And do you remember for disturbance rejection, what would we do? We will say that, let's say RS is 0, and then let's see what's the effect with disturbance, right? And then we will find the relationship for this. So we want the effect of the step disturbance be minimized. So we want a steady state there to also be 0 or minimized. Right? Makes sense? Then what else? If you do that, ESS becomes -1 over K. For this to be minimized, again, this has to be very large. So K has to be large. From here, so I found the zeta for that, right? I haven't evaluated my system if the input is a step. Let's do that. Let's evaluate the system when this. So you see that I'm doing 3 different things you could have done in any order, right? None of them still relate to each other. So in the last one, I'm going to say that, hey, my step input, my input is going to be step. And since I'm only checking that value, I'm going to say that this is 0. And then if you write your transfer function for that, KGS 1 plus KGS times RS. So from the transfer function, if you put all of that values down, you will get this. K times A over S. Now, from here, I know this is 2 zeta omega n, right? Which is K1. And I know this one is omega n squared, which is K. This is the last piece that connects those two together. So far, everything was separate. Now, from here, I say that, okay, 2 times 0.6 omega n is K1. From here, omega n is the square root of K. So K1 is going to be 1.2 square root of K. If you write this K to K1, you will get square root of K over 1.2. So there, basically this is where you don't have to even do that one. So K could be a very large value, but K1 is dependent on K. So let's say choose a large value, K 100. Then we find K1 to be based on that relationship. I think it will be 12 if you do that. So K to K1 becomes 8.33. All right. Now, if you go back here, we had KK1, right, relationship. So I can say ESS is B times 8.33, which is 12% of B. B was the magnitude of my disturbance, right? So whatever the magnitude of your disturbance is, you're going to have a steady state error, which is 12% of that. You can't, in this case, get rid of the error because that's the relation you're going to have. Now, if you increase your K larger, your K1 will be smaller. this value will be smaller, less than 12%. Now you have to look at your system. How much of that is acceptable for me? So if you plot both of this system, the response of the disturbance and the response of your input, you're gonna get something like this. So this would be the response to your input, 1. This is the response to your disturbance, somewhere here, 0.12%, right? So this is your choice. How big you get your K. Now, what does K mean? So you're amplifying, right? Comes with a cost. Amplifiers have their own power supply, which draws energy, right? So how big of amplifier or how much power consumption you want to add to your system for what cost? So you have to look at your system that how much disturbance is okay. Okay, takes a little bit, or what is the nature of the disturbance? Is acceptable 10%? Maybe 10% is good. So you change the K until this is less than 10% and you're done. So, and it says minimize. You never say getting rid of disturbance completely, unless you're designing, I don't know, not like something in NASA, like you have to have absolute 0. Then, yes, you have to add your system, change your system until this is steady state is 0. But if it's minimized, you can define where minimize is acceptable. Make sense? So some problems you can't have a steady state 0 because if you change K is very large, like 10,000, your K1 is very small. But what does 10,000 mean in amplifier gain? Big power supply, right? Is it worth it? Don't know. You're the designer. You have to talk to the engineer that designed and where this device is going to be used. So you'll see that every time you get to design problem, which is all control problems, there's no absolute solution. Your design and your design will be different, but they will keep the system. Okay, so you should have an open mind and not to be afraid of, I did not find the final solution. There's no final solution. All right. So I'm hoping this example makes sense. You don't have to, like, I don't want you to go like, oh, I did not get the same transfer function as you did, because your next problem is going to be a different transfer function. But you need to be able to do this process. That's why I put these examples down here for you. These are from your book, very related to your everyday life. Same things, different conditions, right? Practice what you learn on these two. So don't be hooked up, oh, I didn't get exact transfer function because, well, maybe I did some reduction, or I'm following your book. They definitely did some reduction to get that specific transfer function. The process is something you need to know. All right. Okay, so that was about what we have left. And it's time for a class participation. Yes. So for a class participation, I chose something that relates to last week. If you do it, I can give you some extra information about design that relates to your class participation exam. Okay. So take about 8 minutes, 5 to 8 minutes to solve that. Submit whatever you have. If you're here, you put something down, you get your point. Okay. I want you to think for 5 to 8 minutes on that problem. Okay, so you don't have to have the final solution, but I want you to think about it. There is.
So let's see. As precipitation.
You have 10% error. Okay, not overshoot. 10% error, steady state error is 10%. Overshoot did not. You know why they should have done that? Assume you have a step input. You always start from assuming you have a step input because you want to see the response of the system. You always check the step input. Then assume ramp input. Then check your system and see which one makes sense. That's all. All of the problems from here, the design. All right, I think I'm gonna solve it. It's more than 8, and I don't see many of you know how to approach this. Okay, you all want to submit what you have, is fine. Class participation. So if you are in here, submit because I'm gonna close it. What you have is a class participation. We're gonna 53. All right, I'm gonna just submit. It takes time to submit, okay. I'm just bringing the equations here, so don't worry, I'm giving you time. So your time was up 3 minutes ago, so why you are not submitting? That's the question. Okay, so what is system type? Here, type 1. Do you remember that the table for system type 1? When you have a % error, going to that lecture. Oh, you're not seeing what I'm doing. So why you don't speak? Like, Dr. Z, show the slides. That's what you should say. Because my head is down. We don't know what you're doing. It could be like we don't understand control. Okay? Be very clear. If I do that to you, you complain in SEI, you're not very clear. Seth, I'm talking to you. Stupid. All right. So system type 1, you are in this. For system type 1, in what case you can have a non-zero but constant value error? Only in one case, when you have ramp input. So I didn't need to tell you what the input is. The question told you. So that's how you use the information from the problem, right? Now probably everyone knows what to do. Oh, we have ramp, yes. You know what to do? So system type 1, your denominator had one integrator, right? This lecture here, slide 1. N equal to 1, system type 1. For system type 1, when we have unity feedback, the only case that you have a non-zero steady state error is when you have ramp input. Okay, so now having that knowledge, going back to our beloved lecture, input must be ramp. Otherwise, this would not make sense. So I'm going to put 1 over s squared. I give instead of a 1 because I want to solve this. So ESS is 10%, is 0.1. We already know ESS is 1 over kV. This gives us kV equal 10. We also have equation for our kV. from next table in that lecture, which I'm going to show you again because you look like you don't remember. There. GS is that block. So I'm going to grab this equation and use it in my advantage. So this is limit of S, GS, S goes to 0. This guy is called GS. That's your transfer function of your system. If you solve that and S goes to 0, you will get K times 5 over 6 times 7 times 8, because 0, 0, 0, 0, right? This should be equal to 10. This gives you K672. To have 10% error, your gain becomes this side, right? Now, if your error had to be 0, what kind of input you choose? That, and then you'll find it, all right? Now, so this is 10%. Someone said you cannot have more than 10% error. 10% is minimized, so 10% is good. Now, another example. So everybody submitted, like no problem? Good. So this is another example. Your G of S, let's say, is K times S plus 3, S plus 5 over blah, blah, blah. What system type? 1. Right? System type 1. We need a steady state error of 0.1, which is that 10%. So ESS 0.1. What does it mean? So if you have an input of a step, the output will have 10% error. So it has to be ramped, right? That's why, so if you plot it on MATLAB, this is a ramped input. So amplitude of 20 here, this is your input. Your output is somewhere at this time here, right? So this is your Y, this is your R, RFT, YFT. So you have this much error, 10%. So this is a separate example. I brought this because you can use this, plot it, and see that you have a solution. We haven't done anything yet. I'm just showing you how it would respond. If you do all of that for this, your K becomes 37.3. Is it? Did I run out of time already? I have. No, okay. So for this system, if you do the same thing we did in previous page, just KV is this much, 10 equal to equation for KV, your K is 37.3. So that's 10% error. Now, those are all your equations. So you won't see that big. It's very close, but there's error in there. So go to MATLAB, plot this for yourself. Now, let's say, let's look at a different system, slightly different. K for this new system is 1. This of the transfer function is the same. Now, I want to add an integrator to the denominator. Let's see what happens. So when I add an integrator to the system, what happens? I change the system type. I made it system type 2. Why am I doing that? I want to get rid of a steady state error. I know if I follow that table for system type 2 with a ramped input, the steady state error should be 0. Right? So integrator is just like adding a block 1 over S. All I'm doing is adding this to my system, right? So if you multiply, it's just convolution. If you plot now, this was the point that we saw 10%. There is no error. The output is tracking the input. There's 0% error. That's what we expected. All right. Now, if you look at here, The blue, which was your output, is wiggling a little bit, has some oscillation, and then there's no steady state error. That's the impact of adding integrator to your system. It just increases the oscillation. Why do you expect that? Do you expect that? Why do you expect that? Where is the pole that we are adding? On the imagine, it's on the center, but it's on the imaginary line, right? So we expect to see some oscillation because of that. So you see, 1/S is adding a pole to our system, but that very specific pole is called adding integrator. But we should expect to have some oscillation. Now, if I don't like oscillation, what should I do? What should my system have extra to get rid of the oscillation? Or not oscillate as much? Huh? Think in terms of system and specification. Because keep adding zero and pole, you have to keep adding them, right? What else you can improve your system in your system to get rid of oscillation? Damping. We can increase the damping of a system. So every time we add integrator, then we need to change the damping of the system a little bit. So this is how PID controller works. You add oscillator, it's like, oh, I got rid of a steady state error, but now I have to damp my system. I damp my system, I have a steady state error. You have to find the sweet spot. So this is a nice like introduction to class on Wednesday, but designing controller is just like that. You play a little bit and then you go back and look at your responses. All right. So see you on Wednesday. Review this slide before coming to class. Okay. It's really important.